In the last video, we took a look at phase changes and the heat that was either required to make them happen or that would get released when they did happen. Here we're going to take a look at the ways that heat can be transferred. And it turns out that there are three main channels by which that can happen. And I will go over them from most efficient to least efficient, using as a working example baking a batch of chocolate chip cookies. So the reason why the bottom of a well-made batch of chocolate chip cookies is crispier than the tops is because the cookie sheet itself was made nice and hot, and because it's in direct contact with the bottom of the cookies, heat was transferred by direct collisions between the atoms in the cookie sheet and the bottom of the cookies. This is heat transfer by conduction. It's the most efficient transfer process and involves direct contact between the substances. Now, the reason the tops of the cookies get cooked at all mostly has to do with the cal rod in the oven, assuming you're using an electric oven, otherwise it's the flame. The cal rod of the oven will heat up the air, and this will start a flow of air in the oven. In the way it's engineered in oven, it'll come up along the sides and fall down onto the tops of your cookies. This is why sometimes you'll see cookie recipes say use only a single rack or something like that, is because if you use two racks, the hot air isn't going to be able to make it through the one cookie sheet to get to the other. This kind of heat transfer involves the use of a fluid and gets called convection. It's less efficient than conduction, so that's why the tops of the cookies are still a little gooey and the chocolate has melted but not burned yet. Now, something that you can't ignore, but it is the least efficient channel, is, as we'll see later on, everything that has a temperature will radiate light just because it's hot. This light gets called black body radiation. And so this is why your cal rod is glowing a dull red. It's actually really bright in the infrared, but a little bit of it tails into the visible, and so we're seeing that tail in the spectrum of it in the dull red. But what's wind up happening is that photons of light will get emitted out. They'll say strike the oven wall, get absorbed, and then the oven wall will re-emit. This is part of why preheating is so important, is to get the oven walls up to a consistent temperature. And then eventually, as they rattle around, these photons will eventually strike the cookie. And this is by radiation, which is the least efficient method of heat transfer. But it's misspelled radiation there. There we go. But it's important enough that this is why you need to keep your oven clean. If you let too much splattered pizza cheese or whatever bake onto the walls of the oven, that will change the efficiency with which the light gets both radiated and absorbed. And this will cause some cookies to get a bit overcooked and some to get a bit undercooked. This is why a lot of recipes will tell you to spin the cookie sheet around halfway through, is to try to average that sort of thing out. But then you have the danger that when you open up the oven, all the hot air falls out and or a lot of it, and then you ruin the convection that's happening. So that's not without its own risks. Far safer to just make sure you have a good clean oven when you go and bake your cookies. Now we have good mathematical models for conduction and radiation. Convection, though, is still very much at the dark art stage. Basically, the only way we know how to do it is by direct numerical simulation of the flow. So I'll talk about convection first, mostly just to say you have to model the flows of the individual molecules, but there was a famous result that came out not too long ago that showed, this is from a company that's making computational fluid dynamics software, that showed that the bubbles in Guinness really do fall down. It's not an optical illusion. What's happening is the glass is in contact with the bar, so you wind up getting a heat transfer in at the bottom. This winds up setting up a convection cell because, after all, the beer is a fluid. But it turns out that this convection cell goes up through the middle and down the side, so the opposite of our oven. Like so. So the beer is actually going down along the edges of the glass. And it turns out that the viscosity of Guinness is so high that it drags the bubbles with it. So you're actually witnessing the fluid flow of the beverage getting pulled, dragging the bubbles down, and then all the bubbles shoot up in the middle, which is why you get that really funky head where you see a whole pile of extra bubbles in the center of the head. So I'll leave convection there just because it is that complicated. That, and also to say it can be made more efficient if you say in the case of a convection oven, if you use, say, a mechanical fan or something like that to force airflow, you can make it more efficient, and that's why convection ovens can cook food in less time than a regular conventional oven. But we do have pretty darn good models for conduction and radiation. So let's go take a look at those in turn. So let's start by looking at conduction. So here now, what we're going to imagine is we're going to have what we call a hot reservoir, and we'll define these better in future videos, and a cold reservoir. Basically, just think really big things where the temperature isn't going to be changing too quickly. And then let's just say they're connected together by something. If there's a temperature difference, atoms will collide here, and then along nearest neighbor, nearest neighbor, nearest neighbor, nearest neighbor. And each time, whoever has more kinetic energy is going to lose, whoever's going to have less kinetic energy is going to gain. And so you're going to get a gradient of temperature across the bar. Say this is a rod or something like this. You're going to get a gradient of temperature across the rod as we have our heat flow from hot to cold. And we'll show that later, we'll show that if it's a spontaneous heat flow, it's always from hot to cold. But for now, we'll take that as a statement of faith. So what's going to dictate the rate of transfer? Well, one of them is going to be the difference in the temperatures. The greater the difference in temperatures, the more extreme the difference in the average kinetic energy of each molecule, which means that there will be a greater transfer of energy between successive molecule collisions as you go along, say, this rod or whatever it is. So the rate at which heat is transferred will depend on the difference in temperature. The closer the difference in temperature, the less heat, the slower that the heat will get transferred. We can also see that it should go inversely as the length of the rod or whatever this is. And this is because there will be a longer chain of collisions, which means you give up less energy along each collision, and so that will slow the process up. On the other hand, the cross-sectional area, it should go directly as, because you can be multitasking and having multiple collisions between adjacent atoms at once. And then finally, we'll need some sort of fudge factor that takes into account all the details of the molecular bonding and stuff like that. We will call that fudge factor the thermal conductivity of the substance. So to make the units work, we expect watts here because it's going to be joules per second. So we need to end up with watts. And then we've got 2 power meters here, 1 power meter there, so we need 1 power meter in the basement to cancel. We'll have kelvins here, so I need kelvins there. So this is not millikelvins, this is meters times kelvins in the denominator. Sometimes you'll see instead of thermal conductivities being quoted, they'll quote what are called thermal resistivities. This turns out to be the reciprocal of the conductivity. For instance, when you're buying insulation, the R values are the thermal resistivities. However, they're given in English units rather than metric units. Now, to give you some sense of how these thermal conductivities vary, diamond has a conductivity of about 2,000 watts per meter Kelvin. Normal air is at like 0.023, styrofoam at 0.035. So you can see styrofoam and air make really good insulators because they're lousy conductors of heat. On the other hand, you would not want to, if you're trying to keep your pop cold, you would not want to encase it in a glass made of pure diamond. And what you'll find, like a lot of metals will be at on the order of a few hundred, like aluminum's 240, copper's 400, silver's 430, just to give you some sense there. And it's not a coincidence that if you are a good conductor of electricity, you are also a good conductor of heat. But I'll leave that for when you're exploring electricity more. Suffice it to say, if you're a good conductor of electricity, electrons can flow readily, and the electrons, because they're lightweight, do a great job of heat transfer. All right, so let's just do a quick example of this just to make this concrete. So let's say that this bar is copper. Let's say that it is 0.1 meter long. And let's say this cross-sectional area is 1/10 of a square meter. Let's say the high temperature is 100 degrees C, the low temperature is 20 degrees C, and we would like to know the rate at which the heat is being conducted. Well, the conductivity of copper turns out to be 400 watts per meter Kelvin. So we'll put in our 0.1 square meters over our 0.1 meters. And then our change in temperature, T final minus T initial, that's going to be 100 degrees C minus 20 degrees C. And if you subtract 2 Celsius temperatures, that's Celsius degrees, which are kelvins. But again, if you're not sure, never mistake to add 273 to both of these and subtract. The 273s will end up canceling out. And either way, you'll get that this difference here is 80 Kelvin. And so punching all the numbers through, you'll get that this transfers at a pretty walloping 32,000 joules per second, or 32,000 watts. So you probably do not want to use this as your insulating material in your house. And like I say, I'm not going to treat convection any more than I already did. In general, that can only be handled with lots of painful computer simulation. So we'll instead turn our eyes to radiation. And we call it black body radiation for historic reasons. So all objects that are hot will radiate out some energy as light. And what's going on here is that because you have some thermal energy available, that will jiggle the electrons in the material around, and those electrons getting jiggled around will act just like they're in a radio antenna. Except instead of being radio waves, they'll usually be higher frequency than that, and you'll be emitting light, often in the infrared, but the hotter you get, it works its way into the visible and then eventually out the other side and into the UV. As if the spectrum is peaking in the UV, the tail will be in the blue. So whereas if it's peaking in the infrared, the tail of the spectrum will be in the red. So actually red hot is just kind of the beginning of things being really hot. Blue hot is an awful lot hotter than red hot. Anyway, the rate at which heat is transferred depends on the surface area of the thing. It will depend on the how efficient it can absorb or emit light. So this is the radiation efficiency. This is a number between 0 and 1, no units. So, sorry, it's called the emissivity. Thank you. It's called the emissivity. It's the radiation efficiency. And this is just plain a number that will run between 0 and 1. If the number is 0, you are a perfect reflector. You can't absorb any heat. It also turns out you can't emit any either, so that doesn't happen in practice. And 1 is a perfect absorber, which will both do a perfect job of absorbing heat and also a perfect job of emitting heat. So this is why, for instance, in a hot summer day, if you're wearing a black t-shirt, let's say, the black t-shirt will do a very good job of absorbing radiation from the sun and will make you warm. If you switch from a black t-shirt to a white t-shirt, the white t-shirt does not do as good of a job absorbing the light from the sun. It'll reflect a lot of it out, and as a result, you'll feel cooler. Actually, in a lot of areas that are closer to the equator than they are to the poles, building codes are now starting to require that roofs be a light color, or even just plain flat out painted white, in order to reduce the emissivity so that the shingles don't absorb so much heat from the sun, thus reducing air conditioning loads. In more northern climates, this becomes a bit of a wash, because while it hurts air conditioning loads in the summer, it helps a little bit to reduce heating loads in the winter. So, pick your poison there. And then the temperature here, notice this is not a delta T, this is the absolute temperature. And you must work in kelvins or around Kelvins if you're doing it in English units. Sigma is the Stefan Boltzmann constant, 5.67 times 10 to the negative 8 watts per square meter Kelvin to the 4. And the way I remember this is just to think about like some music dance, a dancer in a musical when they're practicing and you hear the coach start going, okay, from the top, 5, 6, 7, 8. That's how I remember that number. So that's the rate at which you are either emitting heat or absorbing heat. If you're emitting, you use your temperature, and if you're absorbing, you use the temperature of the surroundings. So the net heat flow, or the net rate at which heat gets transferred, because it's a two-way street, will be the difference in the fourth powers of the temperature of the thing and the temperature of the surroundings. So this T naught is the temperature of the surroundings here. This is part of why there's a lot of attention has been placed in designing buildings into thinking about the windows, because it turns out that although windows are clear in the visible, they're actually pretty opaque at other wavelengths. So they actually wind up being pretty good radiators of heat as a result. They have a fairly high emissivity. And so the issue becomes the difference in the fourth powers of the absolute temperatures of the inside of the house and the outside of the house. So even though it may seem like, well, gee, the inside of the house is at 20 degrees C, the outside of the house is at 0, how bad can that possibly be? Well, you're talking about the difference of 293 Kelvin to the fourth power minus 273 Kelvin to the fourth power. And differences in fourth powers get absolutely enormous. Thus, you see all sorts of design tweaks like special films and stuff like that. Film also help reduce the conductivity. That's also an issue with windows by, say, filling the layers in between with argon gas, things like that. But the radiation, the infrared radiation off of a window is a big deal. And similarly, if you're cooling, it goes the other way around. It's radiating heat into the house in that case. Now, it turns out that even though radiation is the least efficient of the heat transfer channels, there are situations where it's the only transfer channel. An example of that would be in a satellite. It turns out that if you were to have a satellite in deep space, or just have a satellite anywhere actually, it's not in direct contact with anything. That would be probably bad. And it's not in any useful amount of air. So convection isn't an option. So radiation's all there is. So when engineers are designing space satellites, they have to work very hard at figuring out how they're going to get rid of all the heat that the electronics on the devices ends up producing. This is why a lot of satellites are coated in gold foil. It turns out that gold has an emissivity that's darn near 1. And also turns out that you can pound gold foil into a really, really thin layer so that you don't have to add very much weight at all to a satellite in order to be able to maximize its ability to get rid of heat. So let's imagine some sort of deep space satellite. Let's say it's operating at 50 Kelvin, which, yeah, that would be really cold, but let's just play with that. And it turns out that deep space actually does have a temperature due to leftover radiation from the Big Bang. It turns out to be about 3 Kelvin. So for our hypothetical satellite, the emissivity is darn near 1, so we'll just call it 1. 5.67 times 10 to the negative 8 watts per square meter, Kelvin to the 4. And then this will be 50 Kelvin to the 4th power minus 3 Kelvin to the 4th power. If you crunch that through on your calculator, you'll find that after you've raised 50 Kelvin to the 4th power, when you raise 3 Kelvin to the 4th power and try to subtract that, you won't really see a difference in the number at all. That's just how drastic these differences in 4th powers can be. And it works out to be 0.709 joules per second. So for this hypothetical experiment that's operating at 50 Kelvin, oops, I'm sorry, I dropped an area there. I imagined we had 2 square meters of radiative area. So for this hypothetical experiment that has 2 square meters to try to dump heat into deep space, it's moving heat at less than a watt, so you better hyper efficiently design the electronics to make that happen. Okay, in the next video we'll start to introduce some ideal gas processes.